The streaming is on, recording is on, and what I can see here when I look at the screen is that seems that my voice goes red quite frequently. So it's possible that the recording quality is not outstanding today. But not a big surprise because every single time we do the recording, there is some kind of problem. And also, I need to give you a warning that it's possible that I go out of the battery because my mic system is giving me a warning that the battery is low all the time. So that might affect the quality of today's recording. The streaming should be all right, but we'll see. We'll see. The last thing that I needed here is that I needed to put the um, picture on. So let me connect this one here so then you can see what I would like to share with you today. So let's see. So this is a laptop. No, this is a HDMI 2. HDMI 2 is this one. And now, I guess what I'm going to do here is that I need your cooperation in today's lecture. And I need your cooperation in the sense that this is how the OBS look like. There's a one important thing that you should keep kind of monitoring. This is how the voice is. And if you see if the voice disappears, you need to let me know. So then that's when we're going to have a break today. I need to go and run and get the new batteries from the department office, and then we will continue. But you're the one that will take care that this recording will be something that if something goes out all the time, and I need to make a final tuning here such that it's not getting red all the time, and I will do that same kind of tuning to this mic system. So hopefully it is all right. All right. So lecture number two. Lecture number two, and today we're going to discuss about spatial multibody dynamics, three-dimensional multibody dynamics. As you will see from the from the course schedule, the plan is that we only going to use 1 week to cover that. And of course, the topic itself is quite extensive. And in order to explain that in details, that would need more than just a week. But I would like to highlight what are the difference between two-dimensional and three-dimensional kinematics, and what is the difference three-dimensional and two-dimensional dynamics. That is an objective of today's lecture. Also, I'm thinking that I will discuss shortly about robot kinematics, and that's something because this knowledge that you can learn today it has a nice application that is related to robot kinematics. So I'm planning to spend a little bit of time in that particular topic, but the main objective is related to three-dimensional multibody dynamics. But now, before getting started, some a few practical matters. This is what I forget to mention last week because there was a question during the break related to exams. There was a question related to then later there was a question related to guided tutorials. So let's first get started with the exams. The exams when you log into the website that is a uni. Oh, I need to change the color. It says a uni.l ut.fi, you can see how is the exam schedules, and you can in this course you can find that there are two different exams. It is a bit confusing because many of you are in the national students, and these abbreviations here they are kind of coming from the Finnish language. Now, two different exams are related or rated as a K and V. This is a symbol of the course, and the K here stands for final exam. How you would know that? Well, the only way to know that is that you need to learn a little bit of Finnish because the K means that it's koe. Is it? I'm not sure, but I think that that's where it's coming from. But it's a final exam. So the K is equal than final exam. Then V here stands for midterm exam. Midterm exam. So that again comes from the Finnish language. And I believe that the V originally means välikkoe. So now you know two words in Finnish. So you know koe and välikkoe. So it's exam and midterm exam. So that's by the way the end of the Finnish class in this course. So we are not going to speak any further Finnish matters, but those are the two things you need to know because you need to be able to enroll the right type of the exam. And if you want to pass the course by using two midterm exams, which is highly recommended. So that's my recommendation. The first one will be end of the February, and then the next one will be in the 8th of May. So those are the two midterm exams. And then if you alternatively wanted to do the full exam, which means that it covers third and fourth period, so the material is everything that I have explained in this class, then it's possible to do that in a 9th of May, or then if not able to do that, then the final opportunity is in October, which is really, really late. Big problem in my mind, because think about this, all the explanations will be, during the spring 2019, and then you go to exam in October. Nothing you ever remember about my explanations. Of course, you can take a look at the recordings again, but highly recommended to take the midterm exams. And if for some reason that's not possible, then the final exam, which is in May, is my recommendation. Now, if you know that you have an issue related to scheduling, so you cannot participate to say first or second midterm exam, then please let me know. So maybe we can organize something. So maybe it could be, I already promised to one of the students that I can organize, the room. The student goes to that room and do the exam, and that will be the one way to do it. Because, if you select this midterm option, then you have to participate two midterm exams. So it's not enough to take just the one, but you need two. Okay, tutorials and the course schedule, that's how it reads. So it says that Mondays we have these lectures, and this is the lecture room. And then Tuesday and Thursday we have guided tutorials. And at the moment we have 32 students in a class. The computer classes, they can take some 20 students. So this week we will organize both of the courses just to see how it's going to be. And it's possible that later during the course, we will skip one of these guided tutorials, but that we will see. But this week, there is Tuesday class and Thursday class. You need to pick one. So pick the one that fits your schedule the best. So again, summary, lectures is for all of you, and then you pick one out of the two guided tutorials, either the one that is on Tuesday or alternatively the one that is on Thursday. So whatever fits to your schedule, time-wise, they both will be in afternoon from 2 to 4 o'clock, and from 2, of course, it's not actually 2 o'clock, but 2:15. That's when it gets started, and it ends at 4 o'clock. Okay, clear? Is this clear? No comments, no questions. Okay, good. So then let's move on. Now, this is a short summary of what we discussed last week, and I'm gonna be brief when I'm summarizing the discussion from the last week, and then we're gonna move on to the world of rotations. And that's gonna be the kind of the core content in the very beginning of the course. And the rotations is something that differentiates two and three-dimensional kinematics, because the rotations in three-dimensional kinematics are quite difficult comparing the rotations in a two-dimensional case, because in two-dimensional case, rotation only can take place around the one axis, whereas in a three-dimensional place, there are three axes where the rotation can take place. Okay, so last week we discussed that in multi-body dynamics, the kinematic notation is based on the usage of body reference coordinate system. So in dynamics, always the dynamics, the idea is to look at the position of particle with respect to reference coordinate system. That's the core material of dynamics. And in order to do the dynamics, we have to first express the kinematics. So we have to express where a particle is located, where is its position, where is its velocity, where is its acceleration. And in the multi-body dynamics, we do all that with help of body reference coordinate system. And in the rigid bodies, the body reference coordinate system travels and rotates with the body. So it's always, it is attached to the body and is welded to body. So if body rotates, the body reference coordinate system will do the same. And in rotation, the body reference coordinates do the same. And now we can define any particles within the boundaries of the body with respect to body reference coordinate system. This is what we explained already in a course that was in the fall. And we can do that with help of vector U bar. But because the vector U bar is expressed in a local coordinate system, we have to convert that to be expressed from the reference coordinate system. And the reference coordinate system, often called global coordinate system, that's the one that is standing still. So it's not traveling anywhere. And all the measurements will be with respect to that coordinate system. Now, how is that we can convert this vector U bar that is expressed by using this coordinate system be expressed in this coordinate system? So we want to express that as a U, not the U bar, because the bar is the one always that's standing, the rotation is in a local coordinate system. Well, we can make that happen with help of the rotation matrix. And the rotation matrix is the one that defines the body orientation in the three-dimensional space. And once we multiply U bar with matrix, rotation matrix A, we can get the U. And that's the trick we need here. That's what makes it possible to have R and U in the same coordinate system, which will be the global coordinate system. And that's how we can define all the particles in the system. And if we can define all the particles, we can describe all the bodies and all the systems, and this is how we can express the dynamics. So that's how it goes. Now, the most cumbersome component, of course, is this one here, which is the rotation matrix. Last Monday, we learned that the one way to express this rotation matrix is, oh, this is the same stuff. So the one way to express this rotation matrix is based on the Euler angles. And the Euler angles is in turn based on three successive rotations. And, my old students, when we meet in a corridor or in Prisma or whatever, we always say this way, hello. But we don't actually say hello, we say respect. This is the way, you're becoming as a member of the camp. So next time you see me or the other members of the course, you don't say hello, but you say respect. Where this is coming from? It's coming from the spatial coordinate system, and it's coming from the Euler angle. So that's what we used to play with. And that's because we are so much into the rotations, we keep our finger in this shape all the time. Each gang, they have their own signs. This is our sign. Okay? Clear? Okay. Now, three successive rotations, how it goes in the Euler angles. It goes in such the way that we have the first rotation that takes place around z-axis. Then there's going to be a second rotation that takes place around x-axis, and then the final rotation around z-axis. Now, important thing is this, that the second rotation takes place once rotated coordinate axis. So that's where the successive is coming from. And then the third rotation takes place twice rotated coordinate system. So that's how we can actually express the rotations based on the Euler angles. The Euler angles, the sequence of rotation, z, x. So I need to reconnect. I need, hold on, I need this one. Settings. Hold on, let me see. QR code is needed again. I practiced this during the weekend, and everything was fine. And now everything is not fine at all. So let's see. Okay, connect it again. Hopefully, I don't need to do that many times today. I can also connect this iPad more directly to my computer, but for some reason that was not very successful today. Okay, so that's what we discussed. Now we discussed shortly as something that is called gimbal lock. A gimbal lock takes a place no matter what sequence of rotation you use. So whatever you have three rotational parameters, and again, the rotational parameters that we introduced in the previous slide, they were, you know, what the heck this is called? Phi, C, you know what that is called, and then the theta, and then the final, this one, C of phi or whatever. Those are the rotational parameters. Now, if you want to make a vector of generalized rotational parameters, just collect these three parameters to one vector, and you can call this vector as a, well, let's call it as a let me make it better. Let's call it as a theta. The theta includes these three components. These are the components, and these are the three parameters that defines the body orientation. So those are the parameters we use. So we have obviously three parameters, but the body can rotate three different ways. So that's the situation. Now the gimbal lock, which takes place if you use three parameters to describe the rotations, that is something that is not a lock. And this is not the mechanical lock, as you know the word lock implies, but it's difficult to express to some of the rotations. It takes place if two of the rotation angle becomes parallel. And the case would be here if you take this tire here, and if you would rotate this disc, let me change the color to make this more visible. So if you would, it's still a little bit unclear. So if you rotate this disc such the way that it will be parallel with this disc, what will happen then? That means that the one of the rotation angle is actually eliminated. So you cannot any longer express the three rotations, but you have instead two rotations. And that's what the gimbal lock is actually standing for. So think about the situation. So let me take this away. Well, here. So think about the situation again where this disc here, which is shown here, is becoming parallel with this disc here. Then it means that I have a rotation around this axis, and then I have a rotation around this axis, and nothing else. So I don't have three rotations, but instead I have two. And this is how it is actually put it in a writing in Wikipedia. And in Wikipedia,